So workshop 10, we're going to do a little bit more on functions and relate this to countability and uncountability. I want to look at one-sided inverses, left inverses and right inverses. So let's see, I'll just remind you what these identity maps on the set are. So id y, defined on y, I'll remind you that id y of little y is equal to y for all y and y. And the same thing for id x, which is from x to x. So that's what the identity map does, or rather doesn't. The identity map doesn't move you, so you stay where you are. Right, so now we knew about, I talked about bijections and inverse functions, but some functions which are not bijections, especially between infinite sets or between finite sets of different sizes, it's possible to have one-sided inverses that are not inverses on the other. So these are not, so it's possible for functions that aren't bijections. They may have a left inverse or a right inverse, a one-sided inverse that isn't a two-sided inverse. On the other hand, we're going to see in a bit that if you've got a right inverse and you've got a left inverse, then you are a bijection and the one-sided inverses were equal to each other. Okay, so G is a right inverse for F. If, when you put G on the right of F, you get the identity map on the relevant place. So since you've got F going this way, F is going from X to Y, G is coming back. F composed with G means you do G first. So you start in Y, do G, and then you do F, you come back to Y. So the only hope of being an identity map is if you're in Y. So that's the same as saying that F of G of Y is the same as Y or Y. But it doesn't force you to be an invert. It doesn't force you to be a bijection, and it doesn't force you to be to be the inverse of each other, because you don't say anything about G of F of X. You don't say what happens to G of F of X. So the other bit that you would need if you wanted to be the inverse function you need G to be a left inverse, that's the one where G of F of X is equal to X, or G composed of F, which means do F first. So you do F first to take you from X to Y, then you do G, come back to X. And if you come back to where you started, so that you've got the identity map on X, then in that case, G, having been written to the left of F and giving you the identity map, G is then called a left inverse. So a left inverse doesn't have to be a right inverse, and a right inverse doesn't have to be a left inverse in general, though there are special cases where, like with matrix multiplication and things like that, where you get certain things for free. So square matrices, if something's a left inverse, it's a right inverse automatically. And if you're mapping from a finite set to itself, you get the same thing, and there are variants like that. But as soon as you move to some maps between infinite sets, and you're not talking about matrix multiplication, then all bets are off. Okay, so your first question, actually, you might as well do question 1 and then question 2, because question 1 and question 2 are almost the same, and you can use question 1 to help you with question 2. So question 1, if you suppose that G is a right inverse for F, so you have to write down what the definition tells you, and then you have to prove that F is also a left inverse for G. That's immediate. Then you have to prove that G is injective and that F is surjective, whenever that happens. But neither of them has to be a bijection, but you aren't asked to give examples. Okay. So then question 2, which you can do using question 1, is you suppose this time that G is a left inverse for F, and then you have to prove that F is a right inverse for G, and then you have to prove that F is injective and that G is surjective. But you can use question 1 and then swap F and G round, so it doesn't take very long to do that. Okay, so we'll come around and see how you're getting on with those two. Right, so I'll say you could use question 1 to prove question 2. You use question 1 and you swap the roles of F and G. The only thing you have to do is about the relationships between them. One being a left inverse of the other is the same as one being a right inverse of the other, but that's not a problem. So let me go back and do question 1. So f of g of x, f of g of y is equal to y for all y in y. That was using the fact that was from our definition. Remember, g is a right inverse for f, so that's back here. G is a right inverse for f. That's f composed with g is the identity. If you put g to the right of f, you get the identity. That's f of g of y equals y for all y in y. So that's what we had before. So we just substitute in the definition. That's always a good start. So that's by definition of right inverse. And it's now immediate that f is a left inverse for g. That's if you put f to the left of g, you get back to where you started. So it's f is a left inverse for g. You have to go back to the definitions of left inverse and right inverse. And since I was talking about g is a something inverse for f, you're going to have to swap f and g and x and y around to say what it means that f is a something inverse for g. Swap f and g and x and y in the definition above to see what that means. Okay. But the interesting bit is the fact that g has to be injective and that f has to be surjective. Right, so let y in y, we want to show that f surjective, f is going from x to y, we have to show that x in x for which f of x equals y. Or in other words, we have to show that y is in f of x. That's to show that the thing's surjective. But y is equal to f of g of y. That's certainly f of something. So that does that one. This shows that f is surjective. This shows that y equals f of x. That's the image of the function. So f is surjective. Okay, what we've really done is shown that everything in y is in the image, but the image is a subset of y, so that bit comes for free. Any questions about that bit, the surjectivity bit? Now to show that g is injective, let y1 and y2 in y with y1 not equal to y2, if there are any, of course. Assuming y's got at least 2 points. Then f of g of y1 equals f of g of y2. is equal to y1 is not equal to y2, which is equal to f of g of y2. Now, f of g of y1 is different from f of g of y2, so it must be that g of y1 is different from g of y2. So since f of g of y1 is not equal to f of g of y2, we must have g of y1 is not equal to g of y2. You could do it by contradiction if you wanted. If g of y1 equals g of y2, then f of g of y1 equals f of g of y2. In fact, you could even argue it directly that way around, as using that version of the definition of injectivity. So if g of y1 equals g of y2, then f of g of y1 equals f of g of y2 by substituting them in, and that gives you y1 equals y2. So that's another way of doing it. Anyway, either way, g is injective. Remember, you can think of injective as meaning 2 to 2. If you take two different points, g has to take them to two different points. So 2 to 2 is not too bad. Any questions about the injectivity bit? Right. That case, we'll move on. So we've question 2, as I said, you just have to swap f of g. You should swap x and y as well in question 1. So let's just see, what did I say about question 2? Use question 1, swap the roles of f and g, so you also swap x and y as well. Then you should just check what happens when you do that. I'll leave that bit to you. Right, let's move on. Now, this proof is actually the same as the proof we had in lectures. So if you find the relevant bit in lectures, you can actually copy the proof. But this is a slightly better result. Okay? In lectures, we proved the uniqueness of inverse functions by this proof, by using one of them as the left inverse and the other one as the right inverse. But this time, I'm not going to assume you're a bijection in the first place. I'm just going to assume that you've managed to find one left inverse and you also managed to find one right inverse, but they might have been different in the first place. And your task is to prove they're equal, and then you then conclude that it's an inverse function, which tells you the original thing is a bijection after all. Or you could also use questions 1 and 2, but I suggest doing it directly. So going from x to y, you've got f, and you've got two functions coming back, a g and an h. Now, g is a left inverse for f, so g composed with f. G composed with f means you do f first, and then g, and that brings you back into x, and so that one is going to be the identity on x. And h is a right inverse for f, so if you put h to the right of f, that means you're doing h first, which means you start at y, do h, then you do f, which comes back to y, and because it's a right inverse, that's going to be the identity map on y. And your task is to prove that g equals h, as a result of which f is invertible and f to the minus 1 is equal to g is equal to h. So it is a proof we did in lectures. You may remember it, or you might have to figure it out again. But remember that composition is associative. So function composition is associative, and you can use that. And anything composed with an identity map is still what it was before you composed it with the identity map. Okay, so we'll let you see if you can do that, and we'll come around and see how you're getting on. Okay, so the hint here as I say, is to look at composing the three functions, which we want to bracket it. We proved that composition of functions was associative, so if you compose g with f, put that in brackets, and then compose that function with h, you get the same thing as if you do g composed with the composite function f composed with h. However, we know that g composed with f is the identity on x, and we know that f composed with h is the identity on y. So we can use that. We have g composed with f composed with h is equal to g composed with f composed with h. That's by associativity of composition. But g composed with f is equal to index doesn't do very much. So g composed with f composed with h is index composed with h, which is h. If you compose an identity map with something, it doesn't change it. While that's supposed to be h. Well, f composed with h is in y, the identity map on y. So g composed with f composed with h is equal to g composed with the identity map on y. The identity map on y it doesn't change anything when you compose with it, so that's equal to g. So what have we got? This one equals this one, but this one is h, and this one is g. Conclusion is g equals h, and the rest follows. So if you find a one-sided inverse, it usually doesn't have to be an inverse on the other side. But if you manage to find a one-sided inverse on one side and you think you found another one-sided inverse on the other side, then in fact the one-sided inverses have to be the same, and the function is invertible, and the one-sided inverses are proper inverse functions. Okay, any questions about that? Which is like something we did in lectures. Right, if not, then let's see what the last bit is. I think I'll just do this one for you. So this is, if you compose surjections, you get a surjection. If you compose injections, then you get an injection. So let's call this one 1 and this one 2. Proof of 1. And remember we've got, so we've got x going to y, going to z, using f and g this time. So we're given that f and g are surjections. We have to prove that g composed with f is a surjection from x to z. Here's g composed with f. Okay? So if we let z be in z, let little z be a big Z, we've got to show that's in the image, that's g composed with f of something. Well, g is surjective, so it's g of something in y. There may be lots, but certainly at least one. That's since G is surjective. And then since F is surjective, we can get to this Y using something from X. And that X is the one which will get you to Z, then G composed with F of X is equal to G of F of X. F of X is Y, so that's G of Y, and that's Z. That shows you can get at everything. This shows G composed with F of X is equal to Z, i.e. G composed with F is surjective. More generally, the image of G composed with F of X is equal to G of F of X. And you might have thought you could have just said that in the first place. So you might have said, well, obviously G composed with F of X is G of F of X of X is Y, so this is G of Y, which is Z, and you're finished. But I think that that's not completely clear that that's a convincing proof. So, but if you think about it, you can prove that G composed with F of X is G of F of X, but I think that could do with 2 lines, just to make sure that because it's a different kind, the way these functions interact, it's worth thinking about anyway. Right. Oh, that was interesting. Well, it's gone all over the place. I think if I go all the way around, I should get where I started. And then if I hit cancel, I should be all right again. Right, what if they're both injective? Suppose F and G are both injective. We have to prove that the composite function G composed with F is injective. This is quite easy. So you let x1 and x2 in X with x1 not equal to x2, if there are any, and you have to prove that G of F of x1 is different from G of F of x2. That's what we're trying to do. We show, well, we have to show G composed with F of x1 is not equal to G composed with X, G composed with F of x2. Let's just rewrite that. We have to show that those are different. Of course, that's talking about G of F of x1 and G of F of x2, because that's what composite does. And we know that F is injective. Since F is injective, we have F of x1 is not equal to F of x2. X1 and x2 are different, so F of x1 and F of x2 are different. But now we use the fact that G is injective and that these two are different. So because these two are different, if you apply G and G is injective, then you're going to be different again. Since G is injective, and just to make it even clearer, and F of x1 not equal to F of x2, We have g of f of x1 is different from g of f of x2. Thus, g composed of f of x1 is different from g composed of f of x2. That happens whenever x1 and x2 and x are different, so that shows that g composed of f is injective. And any questions about those two proofs? I'm going to let you prove this one as an exercise. We're out of time, so exercises to prove this one. We'll stop there. So next week, as I say, we'll be looking at things like the second class tests, the previous exam paper, question sheet 3, things like that, and any other questions that you come up with that you want to ask about.